So, good afternoon or good morning, everybody, depending on where you are, and welcome to our webinar on chiral stationary phases. My name is Guido Krautz. I'm the Business Development Manager at Dr. Maisch, and I'm your host and speaker today. Before we start, some organizational announcements. According to GDPR guidelines, I need to inform you that this webinar will be video recorded. Your names will not be visible to other participants throughout the presentation, but only if you ask questions during the question and answer session using your name. I hope that you consent to these conditions. If you do not, then unfortunately, I need to ask you to leave the meeting now, but I hope that you will stay. Your microphones will stay muted. You have two ways to ask questions during the question and answer session. You can ask questions verbally. In order to that, please raise your hand. There's an icon at the bottom of the screen which says raise hand. So press that and I will unmute your microphone and then you can speak up. And you can also ask questions in writing. In order to that, please click the question and answer icon at the bottom of your screen and type your question, and then I will answer it verbally. All right, so I hope I did not forget anything. Now let's get started, and I will share my screen with you now. Okay, so this is about ReproSil chiral stationary phases. So let's start with some chiral 101. First, let's understand what chirality means. And I have copied here a definition of chirality from Wikipedia, which I will read out to you. Chirality is a property of asymmetry important in several branches of science. The word chirality is derived from the Greek word for hand, a familiar chiral object. An object or a system is chiral if it is distinguishable from its mirror image. That is, it cannot be superimposed onto it. Okay, so when is a molecule or an API chiral? There are several reasons why a molecule could be chiral. Most often, such a molecule has a chiral or a stereogenic center. That means it has an asymmetric carbon atom, as shown here. So this carbon atom has 4 different substituents. And if you look at the mirror image of this molecule, it's not identical with the original. But an asymmetric carbon atom is not the only reason. There are other reasons why a molecule could be chiral, because there is also axial, planar, or helical chirality. And here on the right, you see some examples of molecules which do not have an asymmetric center, but they are still chiral because they are not identical with their mirror image. A molecule could also have multiple chiral centers. And then we get to enantiomers as well as diastereomers. So for a compound that has more than one center, namely n centers, there exists 2 by the power of n stereoisomers. And these consist of 2 by the power of n-1 pairs of enantiomers. So the enantiomers are mirror images of each other. And a pair of enantiomers represents molecules where the configuration in each chiral center is inverted. But then there are also diastereomers, which are not mirror images of each other. So stereoisomers, which are not enantiomers, are called diastereomers. So chirality is nothing unusual. In fact, our whole world is chiral. I mean, I started with the examples of the hands, but many natural compounds are also chiral, and in nature, they are only present in one enantiomeric form, such as amino acids. Natural amino acids are L amino acids. So the enantiomer of that is not a natural amino acid. And amino acids are the building blocks for peptides and proteins. So peptides and proteins are also chiral. Also, monosaccharides are chiral, and these are the building blocks for oligosaccharides or polysaccharides. Another example is nucleic acids, which are building blocks for oligonucleotides such as DNA and RNA, and also steroids. So there would be many more examples of chiral molecules in nature. So what are now the properties of stereoisomers? Stereoisomers, which are not mirror images of each other, have different chemical and physical properties. So you can distinguish them also in chromatography, and you could separate them using normal stationary phases, which do not need to be chiral, for example, C18 or silica. But enantiomers have the same chemical and physical properties, and they can only be distinguished in a chiral environment. For example, chiral molecules have the ability to rotate the axis of polarized light. Some enantiomers also have different flavors. So our nose is in fact a chiral detector, or they can have different effects on the human body. So what is now the relevance of chirality in the pharmaceutical industry? Well, there's one case which is probably always cited under these circumstances, and you may have heard about Contergan. Contergan is a drug which was produced by Grünenthal, a pharmaceutical company in Germany. And it was introduced as a sleeping drug. So the API in Contergan is called thalidomide. And when taken during pregnancy, thalidomide prevented the proper growth of the fetus, resulting in birth defects of thousands of children. So this was a big tragedy. So where the R enantiomer is indeed the sleep-inducing API, the other enantiomer, the S enantiomer, is teratogenic, which caused this terrible side effect. So this and other cases enforced regulations in the pharmaceutical industry to control the chirality of the APIs. So chiral chromatography is in fact very relevant to the pharmaceutical industry because it's used to test raw materials for their chiral purity, and also to monitor enantiomeric excess of a chemical reaction. It's also used to control the purity of the final API and to test for chiral stability of the pharmaceutical, because the API may undergo racemization in the body and thereby form the unwanted enantiomer. And last but not least, it's also used for preparative separation of enantiomers. So how can we separate enantiomers now if they have the same chemical and physical properties? So as I said before, enantiomers can only be separated in a chiral environment. And there are two ways how to do that, the indirect method or the direct method. So the indirect method involves a method to transfer the enantiomer into diastereomers. So, and that can be done by chiral derivatization. So the enantiomer is reacted with another molecule, which is also chiral, and thereby forms diastereomers, which then you can separate by means of achiral stationary phases. Or you could use a chiral mobile phase. So then you have another molecule, which is chiral in your mobile phase. And in such an environment, you can distinguish between enantiomers. Phases, and these allow us to separate enantiomers from each other. So chiral stationary phases are also referred to as CSP as an abbreviation. So there's a large number of chiral stationary phases, and the most popular ones are the so-called polysaccharide phases, which we will mostly talk about today. But there are also ligand exchange stationary phases, protein phases, chiral crown ethers, cyclodextrin phases, Perkel type or brush type phases. So in this case, you have a chiral selector, which is a small molecule, which is chemically bonded to a solid support, such as porous silica. Then there are macrocyclic glycopeptide phases and cinchona alkaloid phases. So as I said, the polysaccharide phases are the most popular ones because they exhibit certain advantages. And these include a wide chiral recognition, multiple chiral selectors are available. So there's a variety of different stationary phases. They usually exhibit high loading capacity and efficiency, and they are suitable for various modes of separation. They also exhibit high pressure resistance because they are silica-based, and they are scalable to prep, and also bulk media are available for large-scale separations. So this is here the general structure of polysaccharide phases. So these polysaccharide phases are based on porous silica gel, which you see down here with large pores. And these silica gels are coated with a polysaccharide. In most cases, this is either cellulose or amylose. And these cellulose and amylose polymers have 3 hydroxyl groups on each monomer unit, and these can be used for derivatization. So through these groups, you can attach your chiral selector. So we have, oh, sorry, there's one slide before. So how does the mechanism of chiral recognition work? So it has been postulated that in order to distinguish between 2 molecules which are enantiomers, there has to be a 3-point interaction. So you can imagine this as a key lock interaction mechanism. So you see that this molecule fits into these holes here. So this is a 3-point interaction, a 3-point recognition, whereas its mirror image does not. And imagine there would only be a 2-point interaction. In this case, it would not be possible to distinguish between these 2 molecules. So it has to be a 3-point interaction. So this 3-point interaction works through various modes of interaction. And in polysaccharide phases, you have 5 possible modes of interaction: hydrogen bonding, dipole-dipole interaction, pi-pi interaction, van der Waals forces, as well as steric interactions. So on this slide, you see an overview of the chiral selectors which we have available. Our chiral stationary phases are called ReproSil chiral, and then the last 2 or 3 letters stand for the type of chiral selector. C stands for cellulose, and A stands for amylose as a polysaccharide. And you see that we have a variety of stationary phases, and I have also put the names of those phases from diCell and from Phenomenex, which are alternatives to these stationary phases. Now, even though phases from diCell, Phenomenex, from us or other suppliers may use the same chiral selector, and they are referred to as clones, this does not mean that they are 100% identical in every aspect. Because not only the chiral selector influences the selectivity and the retention behavior, but also the type of silica gel, the bonding or coating mechanism, and the molecular weight distribution of the polysaccharide. So you will indeed see some differences between phases which use the same chiral selectors from different suppliers. So here's an example of a comparison of our ReproSil chiral OM with the chiral cell OD. So you see that we get similar alpha values, similar selectivity, but we get different retention times. So this is also seen here. Here we even have a little different selectivity, but in any case, they are similar. So this is here from a study from the University of Orléans, which compared ReproSil chiral OM with a chiral cell OD from DiCell. So in this graph, the retention mechanism was compared. So here you see the log K of ReproSil versus the log K of chiral cell. And this shows that these two phases have similar non-specific interaction, non-specific because this is achiral, because all the dots here are on this dotted line. However, when we look at the selectivity, the chiral selectivity, then we see some differences. So here you see the selectivity of our material versus the material from DiCell. Most points are on the dotted line, but you see some points where there is a separation on ReproSil, but not on the DiCell phase, and vice versa, even though these use the same chiral selector. And this may occasionally lead to the fact that you get a separation on one, but not on the other phase. So here we have some examples of ReproSil, Lux-Cellulose 1, and Cellucode from AkzoNobel with our corresponding product. So this is even more pronounced with the phase of JM, which is the clone of chiral cell OJ. And you see it's not really a clone because if you look at the plot here, selectivity versus selectivity of the DiCell phase, the dots are pretty much all over the place. So they indeed behave in a different way. So as I mentioned before, chiral stationary phases and the polysaccharide phases can be used in different modes. So even the coated phases can be used in normal phase, polar organic, reverse phase, and supercritical fluid chromatography. So in normal phase, you use mixtures of alkanes with alcohols. In the polar organic mode, you use mixtures of acetonitrile or alcohol or neat solvent. And in reverse phase, mixtures of water with an alcohol or acetonitrile. We supply columns shipped under reverse phase conditions. So we have different product numbers for those which are shipped in normal phase and reverse phase. And that's because you should dedicate a column to reverse phase conditions, because it's not possible, or at least it's very, very tedious, to switch a column back to normal phase, which has once been used under reverse phase conditions. However, you can switch between the other modes, such as normal phase, polar organic, and SFC. So in SFC, you obviously use carbon dioxide as an eluent, maybe with some organic modifier. So I've referred to those phases I've shown you on the slide as coated phases. And they are called coated because the polysaccharide is only physically adsorbed to the surface of the silica. It's not chemically bonded. And that means that some strong solvents are able to dissolve the polysaccharide and to elute it. So these solvents should not be used with coated stationary phases. And that includes ethers, especially THF, acetone, any chlorinated solvents, ethyl acetate, DMSO, DMF, toluene, ketones, dimethyl acetamide, and IPA in a concentration of more than 50%. Some customers ask me whether these solvents could be allowed as an injection solvent. I would not recommend to do that because anyway, the use of these solvents, even in small amounts, will reduce the lifetime of the column. As a recommended column temperature, we mentioned 0 to 40 degrees, and the pressure stability of the columns is up to 150 bars. So we have also introduced so-called immobilized phases. Immobilized means that in this case, the chiral selector and the polysaccharide is immobilized on the silica, so it's chemically bonded. And that means that you have a wider range of possible solvents which you can use. And that has various advantages. So you can use one of those solvents, which I've mentioned on the other slide, as an injection solvent. You can also use these solvents as a mobile phase. So you can change the influence the selectivity by using more mobile phases. And last but not least, it prevents accidental use of strong solvents. And so the immobilized phases cannot be destroyed by accidental use of one of these solvents. So here are the examples of the immobilized chiral stationary phases. And we have 8 of them. These are equivalents to the phases from dicyl called IA, IB, IC, ID, and IF. And we are currently working on an IG. And Dr. Maisch has introduced to the market 3 phases which have not been previously available from other suppliers. And they are called MOF, MIX, and MIZ. So the coated phases of these are available from other suppliers, but not the immobilized ones. So here's now a comparison of the MIX phase, which is the equivalent to the Lux cellulose 4, but it is the immobilized version of that. The Lux cellulose 4 is not immobilized. And as you see, even though we compare 5 micron with 3 micron Lux cellulose 4, we have a better resolution here, even on an immobilized phase. So this is an example of an SFC application. The next one is an SFC application as well. So here it's just a standard test with TSO. And again, we have very similar resolution. So this is a comparison by a customer. So the molecule here is a real API. And what you see in black is the Lux cellulose 4. And the colored chromatograms are those of ReproSil chiral MIX. So that is the immobilized version of the Lux cellulose 4. And again, you see that in every case, and there are examples here with normal phase conditions, but also polar organic conditions, we have a better resolution on our immobilized phase compared to the Phenomenix phase. So the other unique phase, the MIZ, that's an equivalent to Lux cellulose 2, but again, the immobilized version of that. And again, you see that we get similar behavior, similar selectivity. So how do you develop now a method to separate chiral molecules. Unfortunately, it's not possible to predict selectivity of a chiral stationary phase from the structure of the analyte. So at the end of the day, it's trial and error. You can start with any of the modes I have mentioned: reverse phase, normal phase, SFC, and polar organic, because at the end of the day, they all have similar success rates. Most people would start with normal phase because most people are most familiar with that, but you may also decide to start with reverse phase. So ideally, you screen multiple columns and multiple conditions, because not only are the columns orthogonal to each other, but they are also orthogonal to each other when you use different mobile phase conditions. So you can screen your columns in parallel using a column selector, or in series by switching the column and your mobile phase conditions. So here are some recommended starting conditions for the different modes. In normal phase, you work with mixtures of an alkane, in most of the cases hexane or heptane, with an alcohol, and a good starting point is a mixture of 80 to 20. You can vary then the amount of alcohol to adjust retention time and selectivity. If you work with basic or acidic analytes, then you add 0.1 up to 0.5% of DEA or TEA, and for acidic analytes, you add 0.1 to 0.5% of TFA or of acetic acid. Under polar organic conditions, you work with mixture of acetonitrile with IPA. So a good starting point here would be 95 to 5, or mixtures of alcohols such as methanol and IPA. Good starting point here would be 90-10, or with neat acetonitrile. And again, use the same additives here as before when you work with basic or with acidic analytes. In reverse phase, you obviously work with acetonitrile or an alcohol and water mixtures. The water content has to be less than 85%. And again, when you work with basic compounds, you add perchlorate or TFA. And if you work with acidic compounds, you add perchlorate buffer. Once again, if you work under reverse phase conditions, it's recommended to dedicate a column to this eluent, because it's not possible to switch back to the other modes. So another phase I want to mention here is ReproSil chiral NR. So this is not a polysaccharide phase, but it's a brush type phase. It contains dinitro compounds as a chiral selector, and it is a p electron and donor phase. So the type of chiral selector is similar to that of WELC-01. It's not identical, but it belongs to the same group of compounds. And stationary phase is particularly useful for aromatic compounds, which have a nitrogen or an oxygen close to the chiral center. Also, this phase can be used in various modes, namely normal phase, reverse phase, and in SFC. And there's one more aspect here, because it's a small molecule which can be made in both configurations. So we have two phases which are enantiomers to each other. So in case you want to invert the elution order, you can use the opposite configuration of the stationary phase. So this phase has been very successful at Hoffmann-La Roche. So this is a study which they have published at an SFC conference. And ReproSil chiral NR separates about 50% of their analytes, followed by the other typical suspects such as chiral pack AD and OD and the lux cellulose and amylose 2. So as I said, this chiral selector is similar to that of WELC-01. So we have compared it here with a 5 micron media of WELC-01, whereas we use an 8 micron media of ReproSil chiral NR. So the red line is the ReproSil phase, the blue one is the WELC-01 phase, and you see that in each case, regardless of the different particle size, we get a better separation on the ReproSil chiral NR. And this again is an example in SFC. So at Dr. Maisch, we also sell a couple of other specialty chiral stationary phases, which are not polysaccharide phases. I've mentioned at the beginning protein phases. So we have these two protein phases, ReproSil chiral HSA and AGP. So here a protein is immobilized onto 300 angstrom silica gel. So these phases are very versatile in reverse phase mode. Obviously, the interaction mechanism is complex with these proteins, and there are some solvent limitations. They are not scalable to prep because the loading capacity is pretty low. So here are 3 examples on the ReproSil chiral AGP with ibuprofen, warfarin, and verapamil, all in reverse phase conditions. So another specialty group of chiral stationary phases are cyclodextrin phases, which were developed at the University of Tübingen, which is actually very close to the village where Dr. Maisch is located. And in this case, beta cyclodextrins are immobilized onto 100 angstrom silica gel. We have 2 of them, the one with the native beta cyclodextrin and the permethylated one. So cyclodextrins are oligosaccharides, cyclic oligosaccharides of this structure here. And in fact, they form this kind of cup structure with a cavity inside, which is hydrophobic, and the outer surface is hydrophilic. So apart from these interactions, you see that because of the cavity, you also have steric interactions here. And typical applications are densyl amino acids, barbiturates, propranolol, sulfonamides, prostaglandins, and chlorthalidones. Another useful chiral stationary phase is our phases with ligand exchange. So in this case, a amino acid is chemically bonded to a silica support, and the elution is done with copper sulfate. So this copper forms complexes with the analyte, and this is very useful for the separation of underivatized amino acids. So I've mentioned at the beginning that chiral chromatography can also be used to separate enantiomers on prep scale. A couple of weeks ago, I spoke about our long life preparative column hardware, which is a patented technology by Dr. Maisch. And it's the only pre-packed column on the market with an integrated dynamic axial compression mechanism. So this is realized by a spring mechanism, which is integrated into the column body. So when you pack the column and compact the bed, you also compress this spring. And When a void occurs during the use of the column, then the spring would expand and compensate that void. So long life column hardware has a couple of advantages over columns of the competition, such as Axia from Phenomenex or OBD from Waters. So the long life hardware is packed with a piston. It has a flexible bed length because we can adjust the piston in any position in the column. It's as I said, the only column on the market, the only pre-packed column on the market with dynamic axial compression mechanism. But we can also supply it as a static axial compression column. And we offer packing and repacking service. So once the column has reached the end of its lifetime, it's not wasted. It can be sent back for repacking. And possible column dimensions include inner diameters of 25, 30, 40, 50, and 70 millimeter ID. So here's an example of a scale-up of ReproSil Chiral NR. At the top, you see the analytical column, and then this is a standard column with 20 millimeter ID, but these two are long life columns, and you see that there is a seamless scale up without losing efficiency. So with that, I would like to summarize. I've shown you that different polysaccharide phases are available with multiple chiral selectors, which are amenable to normal phase, polar organic, reverse phase, and SFC conditions, and which show complementary selectivity. I've also shown you that we have immobilized phases, which tolerate a wider range of solvents. Among them are unique immobilized phases, which were first introduced to the market by Dr. Maisch, plus one unique brush type phase, which is the ReproSil Chiral NR. All the columns and bulk media are economically priced. And on top of that, we have a few specialty phases such as ligand exchange, cyclodextrin, and amino acid phases available. So with that, I have finished, and I thank you for your attention. And now I will look into the questions. All right, I see that some questions have been asked already here. So once again, use the two ways to ask questions. Either raise your hand and I will unmute your microphone, or type your question. So okay, the first question here is maximum 150 bars pressure. Yes, this is correct. What about UPLC? We don't have UPLC columns. The minimum particle size we have is 3 microns, but we don't have smaller particles than that. So there are no UPLC columns available. So the next question is here, are some additives forbidden? Basically, no additives are forbidden. Of course, you always have to pay attention to the solubility of your additives, and you have to respect the pH range, which is from 2 to 9. But apart from that, no additives are forbidden. So another question is, which columns are used with polar organic and which type of compounds are separated in above used columns. So all the columns I mentioned, all the polysaccharide columns can be used in all the 4 different modes. So you can use polar organic mode with all of them. It is not possible, as I mentioned, to predict which compounds, which stationary phase is the best for a given separation. So at the end of the day, it's a question of screening. And I wouldn't say that there is any particular group of compound which separates better in polar organic than under different conditions. The main reason why people use polar organic, or at least one of the reasons, is solubility. Because many pharmaceutical APIs are not well soluble in alkanes or in alkane alcohol mixtures. And especially when you do prep chromatography, you need a certain solubility because otherwise you don't have enough loadability. And many compounds are better soluble in those solvents used in polar organic mode compared to normal phase. So I see that someone raised hands. So please feel free to speak up. Hello, you have to unmute your microphone now.
Can you hear me?
Yes.
Yeah, this is Valipan Kandapan from India.
Hello, welcome.
So how are you doing, sir?
Fine, thank you.
And I just logged in. It's a nice overview of the ReproSil chiral stationary phases. It's a nice presentation.
Thank you.
I liked it. I just wanted to log in and listen to you.
All right. Do you have a question, sir?
No, that's fine. I have no questions. I just want to congratulate you on the nice presentations. I need to leave, so I just wanted to say it was a nice presentation, nice overview of ReproSil chiral stationary phases.
Thank you very much. Very kind of you. Thank you.
Thank you for listening to you. Thank you.
Okay. Okay. Someone asks me to send the video recording. I can certainly do that. So tomorrow we will post this video on YouTube. We have a YouTube channel. So when you go to YouTube and you enter Dr. Maisch, then you will find our channel, and then you will also find this video and also the other webinars I have done before about long life column hardware and about mothball. So, all right. So the next question is, in which solvents do you store SFC columns? Dry in CO2 or in methanol? So I would store them in the alcohol which you use as a co-solvent. So in this case, methanol. Yes, that would be a suitable storage solvent. Another participant writes, I have Lux cellulose column. What if my sample contains toluene? It's one of the substrates for the analyzed reaction. Could it affect column life? Or such a low amount of this compound won't be dangerous for my analysis? Right. So in this case, toluene is not a solvent. So in this case, I'm sure it will not harm the column because it will be in an analytical concentration. It will not be a solvent. So in this case, I wouldn't worry. So another question here for ReproSil chiral NR, will there be substantial effects of the temperature on chiral separation? Let's say ambient versus 5 degrees. Once again, this is not predictable, but there are cases where the temperature has a significant effect on chiral separation, to the point that you even see peak inversion. And that's not only with chiral NR, but you may see that also with polysaccharide phases. So one more question is here. How much cost can be saved by repacking a prep column compared to a new column? Well, that depends, of course, on the kind of stationary phase. 20, 30, and 50 millimeter. Yes. So you buy the hardware only once, and once you send back the column, you only pay for the packing service, and that means you can use the hardware multiple times. And yeah, I mean, I can't give you all the prices now here verbally. So I suggest that I reply to you offline and in writing. So and if you can also give me more information of what you are interested in specifically, then I can give you these prices. Next question. Can you provide rough cost for new immobilized column in 250 by 4.6? New immobilized column. Oh, you mean the unique ones, the MIX or the MIZ. Let me just look it up. If I'm not mistaken, it's just below. Yeah. So the price for a 250 by 4.6 packed with a 5 micron material is just under 1,200 euros. So there's another question here. We saw that you manufacture different IDs. Any chance to manufacture 21.2 or others? Well, every manufacturer has different sizes. You see, the 21.2 is a very typical dimension for Phenomenex. If you go to Waters, they would sell you a 19 millimeter column. So we don't have that 21.2 millimeter exactly. So we have 20 millimeter, which would be a standard threaded column, or we have the 25 millimeter ID, which would be or could be a long life column. So, but we don't have 21.2 exactly. So which amount of forbidden solvents can be used on the coated columns? 0.1%. You see, I don't want to give a recommendation now, because as I said, any amount of these forbidden solvents would eventually influence or reduce the column lifetime. Some companies, some customers may use strong solvents to inject their sample, and they get away with it for some time, but you have to understand that this reduces the column lifetime. So even 0.1% would do that. So I don't want to give any recommendation in this respect. The next question is here. Could you be so kind to explain how the column is immobilized? Yeah, how the polysaccharide is immobilized onto the stationary phase. So the exact process is confidential. There are basically two ways how you can possibly do that. You see, when you have that polysaccharide and you want to immobilize it onto the column or onto the silica, then you have to create some chemical bond. And that bond is realized through one of the three hydroxyl groups of the monosaccharide. And that bond can be introduced by either radiation or by a radical reaction. So these are basically the two methods which are described for immobilizing the polysaccharide. Okay, so I have worked on all the written questions now. So are there any more questions from the audience? Anyone who wants to speak up, ask a verbal question? Okay, I wait a few seconds in case someone wants to ask a question. Aha. Oh, it says, thanks a lot for the nice and accessible presentation. You're welcome. Okay, if there are no more questions. Oh, sorry. I just see that someone wants to speak up. So, sir, please.
Hello, Noam Freeman from Israel. I'm curious to know, why can't you change between normal phase and reverse phase through a common solvent? Why is it so strict not to stay with the same set of solvents?
Well, you can at any time change from normal phase to reverse phase. That's not a problem. But it's very tedious to change back from reverse phase to normal phase. It would take a lot of time and consume of solvent to get rid of the water, because you see, what you have is basically a sugar molecule, a polysaccharide, and so once this is in contact with water, it's very hard to elute the water again, and you may have.
Will it affect my?
Sorry, I didn't hear that. Can you repeat that?
I said, will it affect my separation if I were to try to do it, even though, how can I ever be sure that I got all the water out? Let's assume I did my best, but will it eventually affect my separation in a way that it might not give me a true representation of the of what this stationary phase can do under these circumstances, under the new set of solvents?
Yeah, exactly. That's what I meant. I mean, you can never be sure that you get all the water out, and so you may have changed the selectivity of the column, and it will not represent the same as a virgin column, which is used under normal phase conditions, and therefore you should dedicate the column to reverse phase conditions once you use them under these conditions.
Okay, thank you.
You're welcome. Good question here. Any different selectivity you find between your coated and the immobilized phases with the same chiral selector? Yes. So once again, even though the immobilized version and the coated version use the same chiral selector, they are similar, but they are not 100% the same in every aspect. So you may find indeed differences in terms of selectivity between the coated and the immobilized version. And there are studies from various suppliers which suggest that when you compare the columns under the same conditions, then usually the coated phase has a higher resolution compared to the immobilized phase. And that's because when you create the bond during the immobilization process, you lose one of the chiral selectors. So immobilized phase has less chiral selector compared to the coated phase. So this is a very common observation. But then with the immobilized phases, you can use a different set of eluent, of solvent. And so you can get to selectivities which you cannot access using your coated phase because it does not tolerate the solvent. Okay. So there's a question about the chiral NR phase. Is it coated regarding the use of certain solvents? Yeah, so the ReproSil chiral NR is not a polysaccharide phase. So that's a brush type phase, a Perkel phase. So that means that the chiral selector is chemically, it's a small molecule, and that chiral selector is chemically bonded to the silica support. So that column can be used with the usual solvents, and there are no limitations in terms of strong solvents. Okay, someone wants to speak up again? Yes, please. Go ahead.
Thank you again. Noam Freeman from Israel. I was wondering whether there are examples of chiral separation on, the laboratory flash devices that carry a 20 micron particle size as opposed from the standard HPLC 5 micron particle size.
Yeah, our chiral stationary phases are available in different particle sizes, so 3, 5, 10, and also 20. So if you call that flash, then you might call it flash. Yeah, I know some companies introduced flash cartridges, but to me, I mean, chiral stationary phases are expensive compared to, let's say, a C18. So using them in flash is like yeah, a little bit like driving a Porsche in the first gear. Yeah, you could potentially use them for flash, but it would be a very expensive way of doing flash.
But the advantage is self-packing, and you already have the device in your lab, so you would only have to buy the stationary phase. The question is how much it will be affecting your separation, because naturally we're talking about a difference in the not only particle size but also the back pressure is going to be much lower than a traditional HPLC system.
Right. So as I said, our stationary phases are available in 20 micron. They are available in bulk. I mean, if you want to pack them, if you have the equipment in-house to pack them, then there's no problem to do so.
Okay, thank you.
You're welcome. Okay. Any other questions? Okay. So if this is not the case, then once again, I thank you for your attention. Take care, stay healthy, and have a wonderful evening. Thank you.